So now I'd like to take a look at some real world examples just to get familiar with applying regular function things to functions. So exponential functions are extremely useful in modeling real world scenarios that exhibit exponential growth or decay. Now, many of you are like, yes, linear functions, lots of things can model linear function, and that's probably what you're very comfortable with. But there's a lot of things that maybe you aren't as familiar with that require exponential functions to model them. So a few of them, finances. So we'll do some examples of finances to have you recognize how finances require exponential functions. Another one are populations. Population growth is usually exponential, at least for a period of time. So one of the ways to think about exponential growth would be thinking about this b, this base value, this b to the x. So that b, that would be basically how many things would be kind of duplicated from other things. So for instance, if you had something like 3 to the x, or say 2 to the x, for instance, if you had say 2 to the x, when x equals 0, you just have 1. When x equals 1, you have 2. When x equals 2, you have 4, and then you get 8, and then you get 16, and so on and so forth. So you can think about this basically as seeing these, if you had 2 people, they could then have 2 children to have 4 people. And then if those 4 kids each had another 2 kids, then there would be 8 kids and so forth. So you can think about it kind of as this reproduction idea of exponential functions. So populations for a while grow like that. And then what is extremely applicable right now is the spread of diseases. So many of you have probably seen exponential functions. That is all because right now that is how the best way to model the spread of infectious diseases is through exponential function. So we're going to take a look at an example of that, because just to help inform you of the way that this works with disease spread, it does use exponential functions for a while. So the spread of COVID-19 grows exponentially for a period of time. Now, this isn't forever, right? If you think about an exponential function, it's going to keep going up and up and up and up forever, and that's not possible, right? You're eventually going to run out of people. And there's just other dynamics, but at least for a period of time, it does grow exponentially. So the number of cases in Kansas during March and April can be modeled by this. So again, if we just kind of restrict ourselves to a small region, small time period, it can be modeled by this function. So I have 9 times 1.134 raised to the x. So x is going to be the number of days after February 29th. So if you want to think about like the 0th day, that would be February 29th. And then moving forward, day 1 then would be March 1st. Okay, so we're going to find the approximate number of cases in Kansas on each of these days. And so what this looks like is we have to figure out what x value am I plugging in. So x is the number of days after February 29th. So one day after February 29th, this is going to be when x is equal to 1. So I'm going to plug in this. So I'm looking for f of 1, which is 9 times 1.134 raised to the first power. Now this is where you just use your calculator, let that handle these for you. You get 10, or about 10. I'm going to round these numbers because you're talking about people here. So there's about 10 cases on March 1st in the state of Kansas. Then if we go ahead to March 12th, well, then if you think about how many days after February 29th that would be 12 days. So now we find the function value at 12. So I plug in 12 for x. So I have 9 times 1.134 raised to the 12th power. Now if we calculate this, we're up to 41. Okay, so we went from 10 to 41, and we think, okay, that's not too bad, right? I mean, this seems still reasonable. I mean, 40 people getting sick is not too crazy. Now, if we fast forward this to April 7th, so then if we think about how many days after February 29th is that? So there's 31 days in March. So then April 1st would then be the 32nd day, right? April 2nd would be the 33rd day. So you basically take the days in April, whatever day this is, and add 31 to that. So if we take 31 and add on to 7, we're going to be at 38. So I'm going to plug in x is equal to 38. So f of 38 is equal to 9 times 1.134 raised to the 38. And this number comes out to being 1,070. So remember, this is just approximations, right? We obviously can't have specific things, and it's not always going to work perfectly, but approximately these numbers appear. So now all of a sudden we're up to roughly 1,000 people on the 7th. So then if we just look at the 6 days later, right, if we're thinking, okay, well, maybe if we try to add some intuition about how many more, if I just have 6 days later, well, okay, I'm not sure. Maybe you have a guess in your head. So we're going to plug in x is equal to 44. So f of 44, when we plug this into our function, we're going to get roughly 2007. So this number almost doubled in the course of just 6 days. And so this is the reason why there's so much of a goal of trying to reduce the spread of these diseases, because if we allow it to just run rampant, then these types of numbers, this very well could be possible. Now obviously, again, this only works for a period of time. Whether or not it works through all of April, we'll see, but this is a little bit of the math behind the spread of diseases.